Continuing with lesson 7.2, we're now going to integrate uh, involving problems where a natural log will become present. The number one use of or method of integration so far has been a u substitution. And if you look at example 5, you might say that u very well could equal x squared minus 9. There's no obvious antiderivative that we can really identify. And there's no algebra that we can do on this expression. But if we look down below here, this x squared minus 9, do a u substitution, maybe, just maybe, that will help us out. Du will be 2x dx. And if we solve for dx, that will become du over 2x. This integral now will become the integral of, well, we have 4x up above. Down below, we're calling that u. And dx, we just saw, really could be thought of as du all over 2x. Nicely, we see the x's cancel. 2 goes into 4 twice. And we're left with 2 over u du. We can even pull that 2 out in front. And we're left with this integral that we were just talking about right at the end of the first video. The antiderivative of 1 over u in its most general form will be the natural log of the absolute value of u plus c. We're going to, of course, resubstitute back in. We're going to say u is really representing x squared minus 9, and that will be our final answer. So this is how we can do an integral involving a natural log. Notice that there were no bounds. This was an indefinite integral. Jumping to number 6, we see that we have a lower bound of -2 and an upper bound of 1. Again, you might want to let u equal, in this case, 2x plus 7. And if we take a derivative, we'd get du is equal to 2 dx. And we can solve for dx and get du all over 2. But I do want to point out that these boundaries, the lower bound and the upper bound, are in terms of x. And we really need to change those bounds to u if we're going to have a brand new integral. So if you look down below, if x is equal to -2, plug that in for u. If u is equal to 2 times x plus 7, u would be 2 times -2 plus 7. And that's -4 plus 7. That would be u is equal to 3. Similarly, if x is equal to 1, then u would be equal to 2 times x plus 7, so that's 2 times 1 plus 7. That becomes a 9. So this new integral in terms of u will have a lower bound of 3, an upper bound of 9. We'll have 1 over u, but dx now is really du all over 2. I could very well pull a 1/2 out, and I'm dealing with the integral from 3 to 9 of 1 over u du. Now we can proceed with the fundamental theorem. We'll take the natural log of the absolute value of u, evaluated between 9 and 3. In all truth, we don't even need the absolute value for this problem because the bounds are all positive. But even if we keep them in there, that's fine. We'd have the natural log of 9 minus the natural log of 3. And by the way, we could use a property of exponents and say really this is the natural log of 9 divided by 3. We'd have 1/2 natural log of 3, but we can bump that power up high and get natural log of 3 to the 1/2. Another way to look at that is to say we have the natural log of the square root of 3. Okay, last problem. Maybe the strangest looking. We've got the integral of the tangent of x. Well, right now, suffice it to say, there's no apparent u substitution or anything that seems to jump out at us. But if we were to look at tangent as sine over cosine, that really opens up the possibility of doing some other things. I could let u equal the cosine of x, and then I'd have du would equal negative sine of x dx. And we could solve for dx and get du all over negative sine of x right here. And then proceeding, we'd have, well, sine of x up on top. Down below, we're letting u represent cosine, but dx becomes du over the negative sine of x. That's really negative 1 sine of x, but the signs disappear. We could pull that negative out in front and have 1 over u du. This would become negative natural log of the absolute value of u plus c. But of course, our u is really filling in for the cosine of x. So we have the negative natural log of the absolute value of the cosine of x plus c. If you were to look at the back of our textbook, however, you'll notice that in an integral table, this is not the final answer that might show up. There is an alternate form. Really, this is negative 1 multiplied to the natural log of the absolute value of the cosine. And we can, just like we did in our previous problem, take that power and raise it up. So this would be the natural log of the cosine of x, an absolute value, all bumped up to the negative 1 power. But that negative 1 power, cosine to the negative 1 power, is the reciprocal of cosine, which is secant. So here is another form that is just as correct. This is found in a lot of textbooks, but both of the answers I circled are in fact valid. Hope this is going well. Best of luck to you.